Hi, my name is Alyssa Mickle, and I'm currently a junior at the University of Central Florida, majoring in mechanical engineering and biomedical sciences. This summer, as part of the SURF at the University of Florida program, I got to spend 10 weeks researching in Dr. Changlong Lee's lab in the College of Pharmacy's Department of Medicinal Chemistry. IL-6 is a cytokine that regulates the immune response by inducing expression of acute phase proteins and promoting lymphocyte differentiation. Additionally, IL-6 plays a role in energy metabolism as well as bone density homeostasis. With that said, unregulated IL-6 is implicated in many autoimmune diseases and even cancers. IL-6 forms a trimer with IL-6 receptor alpha and GP130. A second, identical trimer dimerizes with the first. The dimer formation is mediated by an interface between the D1 domain of GP130 and the IL-6 of the opposite trimer, forming a final hexameric structure of the receptor complex and activating signal transduction. The Lee lab is working to treat IL-6-caused diseases by designing a small molecule that interrupts the protein-protein interface of IL-6 and GP130. This approach is specific to inhibiting IL-6 pathways and could even potentially be orally active. One approach the Lee lab uses to find new drug leads, which differentiates it from that of other, more traditional methods, is the use of Autodoc for in silico screening. Autodoc models how a ligand will bind to a macromolecule like a receptor. While it isn't a perfect model, it is a great tool for screening a large number of potential drug leads before synthesizing the ones that are the most promising. The program generates many conformations of the ligand and ranks them based on their binding energy. Here you can see several different conformations of a ligand binding to a receptor, with the green lines representing hydrogen bonds. The histogram shows the binding energy of groups of similar binding poses. Once Autodoc screening indicates that a particular molecule has good potential, it is time to start synthesizing it for further testing. While the reaction is running, TLC is used for monitoring. Starting material and reaction mixture are spotted on a silica plate, which is placed in a container with polar solvent. The solvent wicks up the plate, carrying more polar materials further. The plate is then read under a UV light. Over time, a product spot begins to form while the starting material spot disappears. Once TLC shows the reaction is complete, it's time to purify the product. First, the product is dry loaded onto silica gel, and then a rotovap is used to concentrate it. The silica gel is loaded onto a column and product is eluted out into tubes like these in a process similar to TLC. The fractions containing wanted product are combined and concentrated. After your product has been synthesized and purified, its identity and purity can be confirmed using NMR. Here you can see NMR in action. A small amount of dilute sample is put into a tube, which is loaded into the machine. The result is a spectrum which shows the chemical shift and quantity of the various hydrogens in your molecule. Finally, you have your product. That product can be sent on to cellular and animal testing, and additional analogs can be synthesized to optimize binding and ADME properties. I'd like to thank Dr. Lee for welcoming me into his lab this summer, as well as my graduate mentor Daniel Schultz, who's been an absolutely amazing teacher this summer. I'd also like to thank the rest of my lab mates, as well as the SURF coordinators, for making this experience possible. Finally, I'd like to thank UF, the College of Pharmacy, and the provosts for their funding of the summer experience. I look forward to hopefully starting my PhD at the University of Florida in 2021. Go Gators!